All right, good morning, everybody. So picking up from where we left off last day. So just a quick recap. So in the last lecture we were talking about the string class, and we also saw non-static methods. Right? Now remember, when you have a non-static method, you need an object reference to call the method. So in the method contains, that's in the string class, right? Contains searches a string for a substring, right? So what that means is that you need it's non-static, so you need a string reference in order to call the method. So here I've got a string variable called course name, right? Remember, all reference variables in Java are references to objects, right? So course name is a reference to a string, which means I can use course name to call the contains method, right? Contains returns true if that string is part of the string referred to by course name, right? So does course name contain the string CISC? The answer is yes, right? It's case sensitive, so it does not contain lowercase CISC, right? And it does in fact contain the substring 4, right? Now remember, it's a specified substring, and also remember that strings are made up of char, right? So if you want to check does a string contain a specific char, you can't do it by passing in the char, right? Because the contains method expects a string. So you either have to convert the char to a string like that. Right? You could also use string value of if you wanted to, but most people would just use string concatenation, right? But perhaps the better way to do it, if you're really searching for a char, is to use index of instead. Right? So index of is another non-static method, so you need a string reference to call the method. Right? Index of returns the index of the first location of an occurrence of a character in a string. Right? So course name dot index of the char C searches for the character big C in the string, and it returns the first location of big C. Right? So big C is the first character of the string, so it returns 0. If you search for the S, there's only one S in the string, and it returns the first location, so that's 2. Right? The 4 is at the last location in the string, so that's 6. And if the character does not appear, then it returns -1. Right? So if you want to know if a string contains a character, you can use index of and check if the value is greater than or equal to 0. Right? Okay, so if you want to look for the last occurrence of a character in a string, you can use last index of, and it works the exact same way. However, this time it returns it searches the string starting at the back of the string. Right? So where is the last big C in the string? Well, the last big C in the string is there, right? So that's at index 3, right? And the rest of the examples are all the same. Okay, now here's the next very, very significant departure from Python. If you're comparing two primitive values in Java, right, you should use equals equals to test for equality, just like you do in Python. Right? Not equals is exclamation mark equals. Right? What you have to remember is if you have two reference variables, right, then you almost always want to use the equals method instead. You probably don't want to use equals equals. Right? So if you have two reference variables, you almost certainly want to use dot equals to compare them for equality. Right? That's a really big departure from Python. It's something that catches new Java programmers all the time, right? And at the end of the course, there's still going to be some of you writing CISC equals math in this case, instead of CISC dot equals math. Right? Every object in Java has an equals method. Right? So this is one of the methods that every object in Java has, which means you can always write dot equals if you have an object reference. Right? For things like strings, the equals method tests are the two strings equal. So in that case, so you have to look at the documentation for equals to determine what does it mean for two strings to be equal. Right? And so if you look at the documentation, it says two strings are equal if they have the same length and if they have the same sequence of characters. So CISC124 and Math124, they have the same length, but they're made up of different characters, so they're not equal. Right? Little CISC124, case matters, so it's not equal to big CISC124 either. An object is always equal to itself. So CISC dot equals CISC will always be true, right? Math dot equals math will always be true in this case as well. Right? So if you want to test for object equality, you should always default to using equals instead of the equals equals operator, right? It turns out equals equals means something different if you compare two reference variables in Java, right? Very confusing, but that's the way the language was designed. If you want to join two strings together to form a new string, that's the plus operator, right? We've seen this before. So it's called the concatenation operator, right? And it joins the characters of two strings to create a new string, right? So here we've got name 1, it's James Bond 007, right? Name 2 is made up of 3 strings all joined together with the concatenation operator, right? If you actually look at the sequence of characters in the two strings, they're the same. So name 1 dot equals name 2 is true, right? Somewhat confusingly, I'll leave that alone. I'm not exactly sure of the answer here. You can also concatenate primitive values onto a string, right? So if I start with a string, right, I can join, it turns out, not just primitive values, but any other values to the end of the string, right? So starting with a string, I can concatenate the 0 to the end of the string, concatenate another 0 to the end of the previous string, and then concatenate a 7 to the end of the previous string to get James Bond 007 again. Right? And once again, name 1 equals name 3 will be true. Right? It doesn't have to be primitive values over here. These can be anything. Right? So they can be other reference variables, or they can be primitive variables. Right? The concatenation operator will still produce a result. You have to be careful in this case. Right? So the order of the operands here matters, right? Because plus, right, has multiple meanings in Java, right? So if you have a string on the left-hand side, right, then plus means use concatenation, right? But if you have a car and a car, right, plus means compute the sum as an int, right? So that gets computed as an int, and then you add or concatenate a string. Right, so now string concatenation happens, right? But the sum happens first because you've got a plus and a plus, right? The plus operator has equal precedence regardless of the operand types. So the order of operations goes from left to right, right? So car plus car gives you an int, plus a string gives you a string. So you get the int 201 plus the string ha. Right, so you have to be very careful if you're doing this sort of thing. The easy way to solve the problem is to always put the empty string at the front. Right? So if you stick in double quote plus h, the problem goes away. Right? You just have to make sure that the sum gets computed as using string concatenation instead of using, in this case, integer addition. Right? Any questions? Confusing if this happens to you, because when you print it out, you're not going to get the right answer, and then you'll have to figure out what's going on. Right. Okay. In Python, you can slice a string, right? You can slice any sequence in Python. It's one of the nice things of the language. Right? So if I have the string A through G, I can take the slice starting at the second character going to the end of the string. Right? That gives you back a new string, B through G. Right? I can take the slice consisting of the single character starting at index 3, right? So that gives you the D, right? And you can take the slice starting from the sixth character, going up to but not including the seventh. Wait, is that right? 5, 0, 1, 2, 3, 4. Yeah, the fifth and the sixth character in this case. Sorry, 0, 6th and 7th character. Wait, 5, 7. That should give you the 5th and 6th. So 0, 1, 2, 3, 4. Yeah, it gives you the F and the G, sorry. Right. And so that gives you F and G in this case. Right. So you can't use this notation in Java. Right? So Python treats all sequences the same way. Right? You can use the square brackets on them and you can slice them. Even though a string is a sequence in Java, you have to use a string method to compute a substring in this case. Right? So in Java, the method is called substring. Right? It works exactly the same way as a string, as a slice in Python, except that it's called substring, right? And it's a method, so you have to use dot, right? And you cannot use negative indexes, right? Whereas with the slice in Python, you can use a negative index, right? Otherwise, you get the exact same result, right? Substring 1 is the substring of S starting at index 1 and going to the end of the string, right? So that gives you the B through the G. Substring 3.4 is the substring starting at index 3, going up to but not including the 4, right? So that's just the single D. And then 5.7 is the substring starting at index 5, going up to but not including the 7, right? So you have to remember you're always subtracting 1 from that last number. If you want to compare two strings in Python for dictionary order, right, which is called lexicographical order, then you can use less than, greater than, and equals, equals, right? Equals, equals in Python is the equality operator. So all of these examples here will compare, does the string referenced by S, does it come before the string referenced by T in the dictionary, right? So does A become before Z? The answer is yes. Right? Does the A come after the Z? The answer is false, right? And I think that's big T in Python, right? That's big F in Python. That's big T in Python. And is the S equal to the A? The answer is yes, right? So it's true. You cannot use the less than, greater than, or the less than, greater than, or the greater than, less than, greater than, less than or equal to, greater than or equal to operators in Java, right, with strings, right? Those only work with primitive values. So if you want to compare two strings for dictionary order, there's a method called compare_to that you have to use, right? So if you have a string reference S and a string reference T, S dot compared to T compares S and T for dictionary order. Right? If it returns a negative value, right, that means S comes before T in the dictionary. If it returns 0, that means S is equal to T. Right? So in this case, S compared to T and S equals T means they have the same, if S compared to T equals 0, then that's the same thing as writing S equals T returns true. Okay. And finally, S compared to T, if it returns a value greater than 0, means that S comes after T in the dictionary. Right? So it returns less than 0, S is less than T. Right? Returns a value greater than 0, S is greater than T. Right? For compare to, if you get 0, then it means S is equal to T. That's not always true for other types. Right? But for strings, it is true. Okay, so here we've got aardvark and zebra. Right? So if you compare aardvark to zebra, right, so S compared to T, right, then you're going to get a value less than 0. Right? So because aardvark comes before zebra in the dictionary, right? So aardvark is less than zebra. Right? S compared to S is always 0. Right? Compare a string to itself, right? It should always be the same. T compared to S, well, zebra comes after aardvark, so that should be greater than 0, right? Zebra is greater than aardvark. Yep. Yeah, it comes after aardvark in the dictionary. It doesn't matter. It's comparing by dictionary order. Right. Yeah.
Does the return value, is that always the same given two options?
Not for strings. So you have to look at the documentation for the method to determine exactly what the value means. It may not mean anything, right? It may only indicate less than or greater than. For the case of strings, it actually has a specific meaning. So for strings, what happens in compare to is the two strings get compared character by character, right? If they're all the same and they have the same length, you get back 0, right? If it finds two characters that are different, then it returns the difference between those two characters. You don't need to know that. You just need to remember less than or greater than, right? Less than 0 or greater than 0. If you want to replace an occurrence of a character or a substring with a specified character or substring, there is a method called replace. So if S refers to the string sparring with a purple porpoise, right, I can replace all the p's with a t to get a new string. Right? So if I ask the string s to give me a new string formed by replacing all p's with a t, right, you end up getting starring with a turtle tortoise. Right? You can also do this with a string instead. Right? So if s is the string hi ho, it's off to work we go, I can ask s to give me a new string formed by replacing all instances of hi ho with oh no. Those two strings don't have to be the same length. They can be different lengths if you want. Right? And then you end up with oh no, it's off to work we go. Oh, okay. So there are many more string methods, right? So I showed you the documentation for it in the last class, right? And there's like lots, right? There's many methods, right? So there's a lot of methods in the class, right? The ones I've told you about are probably the most commonly used ones. There are other methods that are useful that I'm not going to talk about in a lecture, right? You may have to, at some point, you may be asked some question where it might be useful to look at the documentation for string, or do an internet search to find out how to do the task, right, where you might have to use a different method. Right? But that's part of learning how to use any language, right? You have to learn how to read the documentation. For the purposes of a quiz, though, or an exam, the only testable material is that what appears either on an assignment or in a lecture. Right. Sorry? Okay. So anybody have any questions about strings in Java? I guess the big things to remember are strings are immutable, right? Once you make a string, you can't change the characters in the string. Any method that looks like it changes the characters in a string is actually returning a new string. You probably want a variable to store the return value. If you want to compare two strings for equality, use dot equals. Do not use equals equals. Right? That's going to trap you all. The big problem with equals and equals equals and dot equals with strings is that they appear in a simple program to do the same thing, but they actually do something different. Exactly what they do, I'll explain later in the course, right, when we talk about the equals method. But for now, remember, use dot equals. All right, next lecture is the floating point lecture. So this is deck 6 or 7, I think. 6, lecture slide set 6. Okay. So we talked about the primitive types float, well, we talked about the primitive type double, right? The primitive type float is just a smaller version of double. So it represents a smaller range of values, and in memory, it takes up less memory, right? It takes up half the memory as double, right? So these are the Java approximations to real numbers, right? This is the same approximation that's used in most Python implementations. Right? So Python, when you use a floating point number, you are getting that's the equivalent of using a double in Java. Right? So these are primitive types, so you know that they occupy a finite and fixed amount of memory. And that means you can't represent every floating point number, or every real number exactly. Right? And so that turns out to have some pretty significant consequences. Right? So for example, I can write 0.1 plus 0.1 plus 0.1. Right? And I can write the number 0.3. Right? Mathematically, you know if I write 0.1 plus 0.1 plus 0.1, mathematically the value is 0.3. Right? If you ask Java, is the value of x the same as 0.3, Java will tell you it's false. Right? I guess you shouldn't believe me. You should actually type it into Java at some point. Right? So double x equals 0.1 plus 0.1 plus 0.1 system. I'm just going to print the result. Print line. So is x equal to 0.3? That. I'm going to comment out this other line here too. Right. So we're just going to run these two lines of code. And when you run that, you get false. Right. 0.3 is not equal to 0.1 plus 0.1 plus 0.1. Right, and the new programmer who hasn't learned about how floating point numbers work will say, well, that's weird, right? And we'll probably spend the next 5 hours trying to figure out what they did wrong, right? But you did nothing wrong. It's just the way floating point numbers work. Okay, so here's another example that I really should copy into the editor and show you. I don't have this one, sorry, I don't have this one set up already, so let me just do this. Now you have to be careful when you do this. So if you're copying stuff from the PowerPoint slides, it may not work. And that's because PowerPoint inserts some funny hidden characters. So I'm just going to make a new class. Where are we here? Boop. So make a new class. I forget what it's called. I'll just rename it later. Finish. I'm just going to copy and paste it into here. There we go. Okay, so I need to... Okay, so if you do something like this, so you create a class that has some name, and then later on you decide I want to change the name. So the rule in Java is the name of the class must match the name of the file. Right? So big F floating point, it must be saved in a file big F floating point.java. Right? And that's why Eclipse is saying, hey, there's a problem here. Right? And it even tells you the public type floating point must be defined in its own file. Right? If you hover over that error, you can see that there's an option to fix this. So it says rename the file to floating point.java. That's the one I want. Right? And now that error goes away. Right? So your editor will do a lot of work for you. And I'll show you other tips and tricks as we go along. Okay, so here we got a little program. It's going to use this class called Big Decimal. So Big Decimal is a class in Java that can represent a floating point number using an arbitrary number of digits. Right? It defaults to some large-ish value, but if you want to, you can tell it to use more digits in the number. Right? So what I'm going to do here is I'm going to run that example again. Right? So there's that example. Right? And then I'm going to print out the digits that are actually used to represent 0.1, right? So the way I'm going to do that is I'm going to take that 0.1, I'm going to pass that to, I'm going to make a big decimal object using that value, and then I'm going to ask the big decimal object for what is that string, for the string corresponding to that value. Right? So the method toString, if you call it on an object reference, will give you back the string reference, a string representation of that object. So this gives me a string representation of the big decimal object that was created there. So I'm going to print out 0.1, 0.1 plus 0.1, 0.1 plus 0.1 plus 0.1, and so on and so on and so on. Right? So let's see what this gives us. So let's run the program. And we get the following. All right, so first of all, 0.1 plus 0.1 plus 0.1 is not equal to 0.3. Right? What are the digits that are in the number 0.1? Well, it looks like they're actually that. Right? Notice it's not exactly 0.1. Right? It's 0.1, a bunch of zeros, and then some other digits. Right? You cannot change it to 0.1. I'll explain in a minute. 0.2 is not exactly 0.2. It's 0.20, bunch of zeros, and then some extra digits. 0.3 is not exactly 0.3. So now you can see the problem here, right? If I take 3 of these, right, that's definitely not going to give me 0.3, right? That's going to give me 0.3 and a little bit, right? The little bit, unfortunately, is not equal to that, right? The 0.3 plus the little bit is not exactly equal to that, right? 0.4 doesn't work either, right? 0.4 is 0.4, a bunch of zeros, and then some digits. Oddly enough, 0.5 works, right? And even more interesting is if I actually print out 0.3, you actually get 0.2 and then a bunch of 9s, and then some extra digits. Right. Did I? Okay, so slideshow, continue. Okay, so this all looks very strange, but it actually makes sense if someone explains to you how these numbers are represented on the computer, right? There is an aside here. So the output from that program is a little bit deceiving. So it's a little bit confusing what's going on here. If you have a double value, then you really only have somewhere between 15 and 17 significant digits in base 10. Right? And when I print out the value here, there's many more than 15 or 17 significant digits. Right? So a lot of these digits are actually meaningless. Right? So what's actually happening here, right, is that when I write the value 0.1, right, it gets converted to the nearest double value that can be represented. So 0.1 cannot be represented exactly on your computer, not using a double anyway. Right? So instead, it gets converted to the nearest double to 0.1, but its encoding happens in binary, right? Because everything on your computer is binary, right? What this program is doing is it's taking the binary value and then converting it back to base 10, right? And so when you do that conversion, you can get more than 17 significant digits, right? But really, a double value only has somewhere between 15 and 17 significant digits. Okay, so what the heck is going on? What's going on is that there's a standard for floating point arithmetic, right? So there's a internationally recognized standard called the IEEE standard for floating point arithmetic. It's IEEE 754 and its variations, right? So that's the standard that almost every desktop computer anyway uses to represent floating point numbers. Now, the standard is an enormous document. It goes into great gory detail about exactly how floating point arithmetic should work. Somebody won the Turing Prize in large part for helping develop this standard. It was Canadian, by the way. It used to be at U of T. The Turing Prize is the Nobel Prize in computing science. So obviously, we're not going to talk about everything that's in this standard, but you need to know a little bit about how floating point numbers work. So every floating point number has that representation on your computer, right? So it's some integer value s, right? S is called the significand. It's an integer, right? Multiplied by 2 to some integer exponent, right? So s is an integer, e is an integer, right? And that lets you represent, that is the representation of every floating point number on your computer. So why can't you represent, so 0.1, when I print out its values, it's not 0.1, it's 0.1 and something, right? So I claim that this is the case because it can't be represented exactly if you use this representation, right? And the proof is simple, it's by contradiction, right? So if every floating point number has that representation, right, there must be some integer value s and some integer value e such that that inequality there is true, right? Okay, now the thing on the right-hand side is less than 1, right? So you know that e must be negative, right? Because if e is an integer and s is an integer, there's no way I can multiply those two to get, if e is not negative, then the value of the left-hand side is greater than 1. Greater than or equal to, 1, right? I guess it's greater than or equal to 0, sorry. Right, so e must be negative. Right, so that's 1 over 2 to some exponent e. Right, okay, so let's work this out. So s times 2 to the e is 0.1, so I'm going to assume that's true. Right, I'm going to get rid of the decimal, so I'm going to multiply both sides by 10. Right, so 10s times 2 to the e is equal to 1. Right? I'm just going to divide both sides by 2 to the e. Right? So 10s is equal to 1 over 2 to the e. Right? And remember, e is negative. Right? So I can write 10s is equal to 2 to the minus e, right? Because 1 over 2 to the e is just equal to 2 to the minus e. Right? If e is negative, then this is 2 times 2 times 2 times 2 times 2 e times. Right? Absolute value e times. Right? And so what do you get? You get 2 times 5, which is 10, times s is equal to a bunch of 2's, which is impossible, right? The prime factorization of the left-hand side includes a 5, but the prime factorization of the right-hand side does not include a 5, right? And therefore, this must be impossible. Okay, so you cannot represent 0.1 exactly, even though you can write down the literal exactly, right? I can write down 0.1, no problem, right? But when it gets converted to an actual double value, the conversion has to produce some value s and some value e that is close to, but not exactly 0.1. Okay, so these things called float and double, they are 32-bit and 64-bit binary values respectively. Right. Now, I don't want to write out 32 zeros and ones or 64 zeros and ones. Right? I also don't want to work in binary because nobody can read binary. Well, almost nobody can read binary easily. Right? So if you want to study the behavior of floating point, it's more convenient to switch to base 10. Right? And it's also convenient to restrict the number of digits that you can use. Right, so that's what I'm going to do. So even though I'm going to work in base 10, everything that I tell you about also works in base 2, right, in binary. Okay, so I'm going to only use 4 digits. What does it say? Consider 2 different decimal representations using only, no, not 2. Consider a decimal representation using only 4 digits, right? So this is how, this is the representation I'm going to use, right? I have 4 digits between 0 and 9. That's going to be my significand, so I'm going to use 3 digits in the significand s. Right? To make things simple, I'm going to say that the first digit can't be 0. Right? So in other words, I can't have a number 001 times 10 to something. Right? So that digit here is always 1 or greater. Okay? That just makes things a little easier to analyze. Now I need to get negative exponents somehow, right? In order to represent values that are less than 0. Sorry, in order to represent values that are between 0 and 1. I don't know why I keep on saying less than 0, right? So values between 0 and 1. Right? So to get a negative exponent, what I'm going to use is I'm going to use a digit, 0 through 9, but then I'm going to subtract 5 from it. Right? And my exponent will be the result of that difference. Right? So if the largest value of d4 is 9, then my exponent is somewhere between 4 and minus 5. Right? So if d4 is 0, I get minus 5. So that's how I get negative exponents. Right? This is called that thing there is called the bias, if you're interested in. So that's going to be my representation, right? I get 4 digits. To convert those 4 digits into a floating point number, I do that little math there. Okay, so there's a whole bunch of implications that arise once you decide to write your floating point numbers this way. Right? So I get 4 digits, right? So I can write out the number, for example, 100 times 10 to the minus 5. Right? If I convert that to a decimal value, that's 0.0100. Right? That's the smallest number that's the smallest positive number that I can represent. Right? That's the smallest spot. Notice that when in this particular example here, because I'm saying that d1 can't be 0, I can't actually represent 0 exactly. Right? So the smallest positive value that I can represent is that number there, right? 100 times 10 to the minus 5. Right? And so now you can start to ask other questions, right? So if that's the smallest number, what's the next larger number that I can represent? Right? Well, the next larger number I can represent is, well, I can change that 0 to a 1 to get 101 times 10 to the minus 5. Right? And so that gives you the decimal value, 0.00101. Right? If I look at the difference between these two values, it's 1 times 10 to the minus 5. Right? You say, okay, that's interesting. Right? So I can represent that number, and I can represent that number, but I can't represent anything in between those two numbers. Right? Notice that the distance between numbers is that. Right? Now what happens if I change the exponent? Right? So what happens if I go to the exponent minus 4? Right? The smallest number that I can represent using the exponent minus 4 is 100 times 10 to the minus 4, right? Which is 0.01. Right? The next larger number that I can represent using an exponent minus 4 is 101 times 10 to the minus 4. Right? And so now the difference between those two numbers is 1 times 10 to the minus 4. Right? So notice what's happened here. The spacing between adjacent numbers has changed. Right? Here, the distance between two closest numbers is 1 times 10 to the minus 5. Now it's 1 times 10 to the minus 4. Right? So not only can I not represent every floating point number, the distance between floating point numbers is changing. Right? If you increase the exponent to 10 to the power 2, right, then the smallest number you can represent using the exponent 2 is 100 times 10 to the 2. Right? That's 10,000. Right? The next largest number is 101 times 10 to the 2. So that's 10,100. Now look at the distance between two numbers. Right? It's 100. Right? I can represent 10,000, I can represent 10,100, but I can't represent any number in between. The distance between those two values is 100, which is much bigger than that and that. Right? And if you go to the 10 to the 4, you get a similar result. Right? I can represent 1 million, I can represent 1,010,000, I can't represent any number in between. Right? The distance between adjacent numbers is now 10,000. Right? So the spacing between adjacent number changes based on the value of the exponent. Right? Notice that the difference here is just equal to the power, is just equal to 10 to the exponent. Right? So the difference between adjacent numbers here is 10,000, but that's just 10 to the 4. Right? The difference here is just 100, but that's just 10 to the 2. Right? Strange, but true. This is the way floating point numbers works on your computer. Okay, so the distance between adjacent floating point values changes depending on the value of the exponent. Right? That distance, right? The distance between two adjacent floating point numbers is called the ULP, right? Or the unit in the last place. Right? Why is it called the unit in the last place? Because right, the last place in the significand is the digit on the right. Right? So if I set that value to 1, that's equal to 1 ULP. Right? So 1 unit in the last place. Right? And it turns out that the ULP is the one of the ways of measuring error in floating point values. You can actually get the value of an ULP for any double or float value using the math class. Right? So math.ULP, some value, will tell you the difference, the distance to the next closest floating point value. All right, so if I write some floating point number down as a literal, right, and then that number gets converted to the closest value that can actually be represented, right, there is usually going to be some difference between those two values. Right, so if I want to know what that difference is, you can calculate that in a bunch of different ways. Right? So one way you can calculate that is to use the absolute error. Right? So if x hat, if that's my true value, right, and x is the approximate value, right, then the absolute error is just the difference. Take the absolute value of those two values. Right? So for example, I can't represent 0.1 exactly on my computer. Right? So the absolute error will be 0.1 minus whatever the floating point representation of 0.1 happens to be. Right? Whenever you have whenever you type in some real value that you, so whenever you type in a double literal, right, when that gets converted to an actual value on your computer, right, the error is up to 1/2 of an ULP. Right? But you can see this, so you can see this just by looking at the table. Right? So that difference in that column there, that's the magnitude of 1 ULP. Right? So 10,000. Right? So if I write some number that is between 1 million and 1,110,000, right, the closest I can get to an actual value is either that one or that one. Right? I can't represent any value in between. So if I write down, say, 1,005,000, right, then it gets converted either to that value or that value, right? And the difference is 5,000, right, which is 1/2 of the difference, right? Right. So if any value in between these two values here gets converted to the closest of these two, right? The distance to the error that you get is equal to half the distance between those two numbers, right? Or 1/2 of an ULP. Okay. All right, so now when you're actually working with the floating point numbers, right, if you want to compute an error in ULPs, you take your true value, right, and you write it using our floating point representation, right? So in other words, you write it using a significand and exponent, right? So in our case, we're going to write it with 3 digits for the significand and 1 digit for the exponent. Right? Now, when you write out your approximate value, you're going to do the same thing. However, you're going to make sure the exponent has the same value as the real value, as the true value, right? And then you compute the difference, right? Okay, so let's look at an example. All right, so suppose I have a value 1.29, right? And I have some other value that's the approximate value of 1.25. Right? If I want to know what is the error in ULPs between these two things, right, then I need to write this thing out, write the true value out using my floating point representation. Right? So I take the 1.29 and I say, well, I need 3 digits for the significand. So that's 1, 2, and 9. Right? I need to make sure that this value here is equal to that value there. Right? So that's 129 times 10 to the minus 2. Right? So that thing there, that's my floating point representation of the true value. Right? Now I'm going to do the same thing with 1.25. However, I have to make sure that exponent is the same as that exponent. Right? So in this case, it turns out it's 125 times 10 to the minus 2. Right? And now you subtract the two values. That's just 4 times 10 to the minus 2. Right? That number 4, that's the number of ULPs of error. Right? So there's 4 ULPs of error between 1.29 and 1.25. Right? Okay, so that was simple because it turns out both of these numbers, when I write them out, they have the same exponent anyway. But if I have two values where their order of magnitude is different, then the exponents are going to be different when I write them out using their floating point representation. Right? So if I write out 0.5 using our floating point representation, I'm going to get 500 times 10 to the minus 3, right? 500 times 10 to the minus 3. But you can't do it that way, right? You take your true value and you write it out, right? So that's 121 times 10 to the minus 1. Now you take your other value and you write it out, making sure the exponent is the same as the true value. Right? And I need to do this in order to compute the number of ULPs correctly. Right? So that's 5 times 10 to the minus 1, right? Which is not a valid representation in our number system. But to compute the number of errors, this is the way you do it. To compute the number of ULPs of error, this is the way you do it. Right? So that's 5 times 10 to the minus 1. Do the difference. That's 116 times 10 to the minus 1. Right? And so there's 116 ULPs of error between these two values. Okay, if you have if your true value is actually some real number, like pi, for example, right, as opposed to a floating point value, then you just keep all the digits, right? So you don't care. You don't have to strictly use our representation for the true number, right? You need to make sure it has the right number of digits in front of the decimal place, right? But if you have extra digits, you can just write those out. You just write out the extra digits. Right? So 59,287 point something is equal to 592 point something times 10 to the 2. Right? 58,900, I just write that out, making sure to keep the exponent the same as the 2. Right? So that's 589 times 10 to the 2. Right? And here you get 3 point something ULPs of error. Right? So once again, that exponent has to be the same as that. Right? If your true value has extra digits in it, more digits than you have in your significand, you just keep all the digits. Right? There's also something called relative error. So relative error is just the absolute error divided by the true value. Right? If someone asks you to compute the relative error, right, you don't compute the relative error using your floating point representation. Right? You use real math to compute the relative error. But we're not going to look at relative error in this course. Okay, so where all of this starts to make a difference is when you start to add and subtract floating point numbers. Right? What you have to remember here is that you only have a fixed number of digits to represent your numbers. Right? So if you add or subtract two numbers, it's not unusual if the number of digits in your result changes. Right? But you can't represent all those digits, so you're going to run into a problem. So to add two floating point values, right, if they have the same exponent in our representation, then you just add them. Right? So 12.1 and 63.8. So take the 12.1, convert it to your floating point representation. Right? 3 digits, so that's 121. Compute the exponent, that's 10 to the minus 1. Right? Same thing with 63.8, so just write out 63.8 as 638 times 10 to the minus 1. Right? Now compute the sum. Right? So that's 759 times 10 to the minus 1, right? Or 75.9. 81,500 and 13,600. Right? Write them out using our representation. So it's 815 times 10 to the 2. Right? 136 times 10 to the 2. Add them up just like you did in grade school. Right? That's 951 times 10 to the 2. Okay, now what happens when your result produces an extra digit? Right. Okay, so if I take two numbers, add them, and I end up with an extra digit like I do here. Right, so now I end up with 4 digits in the significand. Right, I now have a problem, right? Because I can't actually represent those, I can't use 4 digits in the significand in the result. Right? And so what we're going to do is we're going to round that result to remove the extra digit. So here's 82.1 and 63.8. Right? 82.1 is 821 times 10 to the minus 1. 63.8 is 638 times 10 to the minus 1. Do the sum, and I get 1459, right? 4 digits, which I'm not allowed to use. I can only use 3. So I'm going to round that value to 146 times 10 to the 0, right? So round that to 1460, and then shift the exponent 1 position, right, to get 146 times 10 to the 0. Right? So notice what has just happened here. Right? The real answer is 145.9. Right? But I can't represent 145.9 in our representation. Right? The closest I can get is 146. Right? So I can't even add 2 floating point numbers without there being some error in the result. Same thing, so 81,500 and 93,600. Right? Write them out so that they have the same, write them out in their floating point representation. Compute the sum. Here I get 1751 times 10 to the 2. There's too many digits, so round this to the second significant digit. Right? You get 175. Adjust the exponent by increasing it by 1. And you get 175 times 10 to the 3. Right? Once again, I can't compute the sum of 2 values exactly, even though I can write out both operands exactly. Right? I can write that value out exactly in our representation. I can write that value out exactly in our representation. I can't compute the sum exactly in our representation. Okay, now you might ask, what happens if the 2 operands have different exponents? Right? And so the rule is always use the larger exponent. So 4,320,000 is 432 times 10 to the 4. Right? 12.1, well, that's 121 times 10 to the minus 1. But I have to make sure that the exponents are the same. So we always use the bigger exponent. So that becomes 00121 times 10 to the times 10 to the 4. Compute the result. Right? 432 point a bunch of stuff. Right? I can't use I can't use any of the digits after the decimal point. So round the result. Right? So that rounds to 432 times 10 to the 4. Right? Notice that to compute this sum, right, I need 8 significant digits. Our representation only has 4. So it's impossible to compute the sum exactly. All right, so it's 20 after the hour. I'll stop there and finish off this lecture in the next class.